So in the previous lecture we had ended the previous lecture with this exercise. So let's just do this exercise. So what do we have? Let's make a picture of this. So let's say we have Rn. So this in our case, let's just take R2, and we fix this point A comma B, and we want to show that the complement of this point. So we are leaving out this point. So we want to show that the complement is an open subset, right? So let's just take any point x comma y, right? And then, so okay, so how will we prove this? So let x bar x m in Rn be in the complement of this point. Right? What this simply means is that x bar is not equal to a bar, which implies that there is some I such that xi is not equal to ai. Right? So let epsilon be the absolute value of xi minus ai. Right? And this is positive. Yeah. So we claim that S epsilon by 2 of x is completely contained inside Rn minus this a1 up to am. Right. So in other words, we are taking this distance epsilon, this epsilon, and we are taking a square. Let's just, to be safe, let's just take epsilon by 4, right? So we are taking this s epsilon to the by 4 around this point x comma y. Okay. So let's prove this. So suppose if y equal to y1 up to ym belongs to s epsilon by 4x, so then this implies that mod xi minus yi is strictly less than epsilon by 4, right? But then this implies that so this implies that yi, it cannot be equal to ai, right? Because xi minus ai is equal to epsilon. Yeah. So therefore, this implies that y belongs to Rm minus a1 up to am. Right? So this proves that this thing inside in the complement, given any point in the complement, we have found a basic open subset which contains that point, and it's completely contained inside the complement. So therefore, the complement is open. So this implies that is an open subset. Is an open subset. Yeah. So this implies that Rm minus A is an open subset, which implies, by the definition of closed subset, a singleton is a closed subset. Okay, so with this, let us begin the next lecture. So in this lecture, we will define the closure of a subset. Yeah? So let's first write the definition, and then we will see what this means by means of some example. Okay, so let A contained in X be a subset So it can be any subset, it doesn't have to be open or closed. Yeah. So the closure of A is defined as follows. Right. So A closure is equal to those points in X such that for every open set, or rather if U is an open set, U is an open set containing X, then U meets A. U intersection A is non-empty. Okay. Let's try to understand this by means of an example. So the simplest examples are on the real line. So let's take the real line with the standard topology. Yeah. And we can take the interval 0, 1. Let's take this interval 0, 1 and let's see what its closure is. So suppose we take any x which is not 0 or 1, let's say x is strictly less than 0. So then we can find a small neighborhood around x which does not meet this interval A. So A is equal to this open interval 0, 1. Right. Similarly, if we take any, so this implies that if x is strictly less than 0, then x does not belong to A closure. Yeah, because the closure requires that every neighborhood, every open subset which contains x should meet our set A, right? And similarly, if I take any x which is strictly greater than 1, then also we can find some epsilon small enough such that the epsilon neighborhood doesn't meet A. So once again, this implies that if x is strictly greater than 1, then x does not belong to A closure. Okay. And let's make a remark. Maybe I should have made the remark here itself. Remark. It is completely obvious, or it is clear that A is contained in A closure. Okay, so let me just highlight that remark. Okay, so therefore, A closure. So in this example, A is contained in A closure, and A closure has to be contained in this closed interval 0, 1. Right? That's what we have seen, because if we take anything which is strictly less than 0, then it's not in the closure. If we take anything which is strictly greater than 1, then also it's not in the closure. The only possible points which could be in the closure are 0 and 1. So let's see if they satisfy the definition of a closure, of being in the closure. So if we take 0, then no matter which neighborhood of 0 we take, if we take any open subset, so if U is an open subset which contains 0, right, then by the definition of the topology, then there exists an epsilon positive such that d epsilon 0, the ball of neighborhood radius 0, epsilon around 0 is contained in U. Right? But clearly, epsilon by 2 belongs to this ball, and epsilon by 2 is contained in 0, 1. Right? So this implies that U intersection A is non-empty. Right? So therefore, 0 is contained in A closure, and similarly, one can check easily that 1 is contained in A closure. Right? So therefore, A closure in this case is precisely the closed interval 0, 1. We can give a slightly more complicated example. So let's give an example in R2. So we can take this region, right. So this region is A is equal to those x comma y in R2 such that x square plus y square is strictly less than 1. Yeah, and I won't write the details, but you can check that if we take any point x comma y, a comma b, let's say, such that a square plus b square is strictly greater than 1, then we can find a small neighborhood which does not meet a. Yeah, then there exists epsilon positive such that S epsilon a comma b intersection a is empty, right. And similarly we can check that if a square plus b square is equal to 1, then for every epsilon S epsilon a comma b intersection a is non-empty, right. So this will show that a closure is exactly the set x comma y in R2 such that x square plus y square is less than or equal to 1. Yeah. Note that A is obviously contained in A closure. So A closure is just adding the boundary, this boundary circle to A. Okay. Yeah. Okay. So as we proceed, we will get more familiarized with this notion. So for now, let's prove a lemma. So although we will write a proof, it's good to keep a picture in mind while we prove these statements. So let A contained in X, like for instance a picture in R2 will be good enough, be a subset, then A closure is closed in A, is closed in X. So that's why the word, so this justifies the name closure. Okay, so let's prove this. So it suffices to show that X minus A closure is open. Right, the definition of a closed subset was the complement should be open. So that's what we are going to show, that the complement is open. So let us pick, so let X be an element in X minus A closure. Right. So that is what this means, that X does not belong to A closure. But then by the definition, so then by definition there exists an open set U containing X U contains X, or which contains X, which contains X, and U intersection A is empty. Right, but it follows that if Y is any point in U, right, so then Y has an open subset which is U itself, which does not meet A. Yeah. then Y has an open subset, namely U, which does not meet A. Right? So thus Y is not contained in A closure. Right? So therefore we have proved that. So this implies that U is completely contained inside X minus A closure. Right? So thus for every X in X minus A closure, we have found an open set U sub X, which contains X, and U sub X is contained in X minus A closure. Right? So therefore, this implies that this X minus A closure, we can write it as union X minus A closure is U sub X. Right? And each of these is open, and an arbitrary union of open sets is open, so this implies that X minus A closure is open. Okay. So roughly this says that if we take any point here, we can find this small neighborhood which does not meet the closure, and similarly if we take any point here, and the complement, which is this open region in red, is open. Okay, so let us prove this proposition, the next proposition. Let us use this lemma to prove the next proposition. A set A is closed if and only if A is equal to A bar, yeah, or A closure. Right? So let us prove this. So let's just recall the definition of this A bar. So X is in A bar if it has the property that given any open subset U which contains X, it should meet A. So let's prove this. So let us first assume that A is closed. Right? So we need to show that A is equal to A closure. Okay. So since A is contained in A closure, we already know this is obvious. We had observed this in the remark which followed the definition. It is enough to show that A closure is contained in U. Okay. So taking complements, so to prove this, to show this, it suffices to show that X minus A closure contains X minus A. And which is what we are going to prove. Okay. So let X belong to X minus A. Right. So as A is closed, it follows from the definition that X minus this implies x minus a is open. Yeah, so let us denote this open subset by U. Right. So thus there is an open subset namely U, which contains x and such that U intersection A is empty. Right? U is defined to be the complement of A, so therefore U intersection A is empty. Right? So thus x does not belong to A closure, A bar if you like, yeah, by the definition of this A closure. Yeah. So this implies that x belongs to x minus A. So thus we have proved that we have proved this, and therefore we have proved this, right? Okay. So this implies that A is equal to A bar. That proves one direction of the proposition. So for the other so next let us assume that A is equal to A bar. Right. So then by the previous lemma, so what did the previous lemma say? The previous lemma said that A bar is closed in X, right? A bar is closed in X, right? And since A is equal to A bar, so thus A is closed in X. Which is exactly what we wanted to prove, right? We wanted to show that A is closed. Right? So this completes the proof of the proposition. Okay. So as a corollary, as an easy corollary, yeah. So let B be a subset of X. Yeah. So then B closure, yeah. So closure of B closure is equal to B closure. So if we take closure, then taking closure again makes no difference. So let's see how to prove this. So proof. Right. So from the lemma, so the lemma says that this lemma over here, it says that no matter which subset we take, the closure is always closed in X, right? So applying this lemma, from the lemma we get that B closure is a closed subset, right? And this proposition, yeah, the above proposition, says that B closure is closed implies B closure is equal to B closure closure. Implies that B closure is equal to B closure closure. Yeah. So applying the previous proposition, by taking A is equal to B closure. Okay. So we will end this lecture with two easy exercises. So let A contained in B be subsets, then A closure is contained inside B closure. That's the first exercise. And the second exercise is, so let Z contained in X be a closed subspace, and let A be a subset of X which is contained in Z, yeah. So then A closure is contained in Z. Okay, so let me make a remark. So exercise 2 says that A closure is exercise 2 and the above lemma. Imply that A closure is the smallest closed subset. Containing A. So we will end here.